Hi, this is a video about linearization in IB physics. I'll tell you what it is, why it is important, and how we can do that. Alright, let me give you an example. Let's say you want to study the free falling object. So I have released an object from rest and I'll try to measure its time and also the displacement along the whole motion. So previously in our lesson, you probably have learned video analysis, and of course that is a tool for us to use the software to automatically generate the velocity time graph and also acceleration time graph, and maybe you can find acceleration through that. But now this is another approach to find out the acceleration as well, and also relationship between time and displacement. So what you can do first of all is of course after you got the data you want to plot in the graph. But one thing that I will want to just tell you by the way is that when you present the data, they should all be in the same decimal point, like what you learned in IGCSE paper 6. In your exam report, lab report, that means your internal assessment as well, you should be aware of these as well. So for example, for the data that is 0 and also 1 here, this is actually 1.0, right? Because maybe for the time, of course these data I make it up, but then maybe it has an uncertainty of plus or minus 0.1, and for displacement will be plus or minus 0.01. And so for my data, I should present them in all the same decimal point. So this should be 1.0, and you can also see here, all right, this one should be 2.40 instead of 2.4 only. So one thing that you can do with Excel is you can simply highlight them, and there's a button you can allow you to change its decimal point, all right, with all the selected cell. So I would like to keep it as 1 dp, and this one will be 2 dp. All right, 2 dp, like here. Okay, so this will be much more organized and correct in physics as well. And so the next thing you want to do is simply proceed with the graph. Since you are using software, then you can just plug it directly, and from what you see, like by your eyes, you can see that this is not a straight line, so it's obviously a curve. So if you try to plug it on a piece of paper, obviously you will want to draw a curve onto that. And so if you try to add a trend line from the Excel, they will tell you, I mean, I don't know why, I don't know whether they have actually put any thoughts onto this, but then obviously this is not a linear line, so don't just accept whatever the software given to you. Remember, you are the one who learn physics, who learn about data, and you are the one who are the human, so don't let the software to just override your thought. So that's first thing, right? You look at the empirical data. That means this one, although these are not real, I make it up, but let's say you really did the experiment, so these are the empirical data, and from the graph you can tell it is a curve, so you should not proceed with a linear line. Secondly, there's also another thing you can consider is the theory. Okay, so it's a theory and also the reality, the empirical data and the theoretical framework. In terms of the theoretical framework, you should have remember that something we learned in kinematics is S equal to ut plus half at squared. So according to this, then the relationship between S and T will be proportional, like S will proportional to T squared instead. Especially for me, I would say the experiment, I would actually release the object at rest. So U actually will become 0. So what you reduce this equation to will become only S equal to half gt squared, because I'm doing free falling, right? So A will simply be the gravity. And so if this is what I expect in terms of the theoretical framework or the model that I'm thinking, of course there may be some assumption like there's no air resistance involved here, then according to this graph, since we have the x-axis to be the time, this is t, and this is gonna be s, because normally we'll put the independent variable, because time is probably the independent variable you decide, and the displacement is the dependent variable, whatever you can measure at that moment. So that's why we put it in the y-axis. They should have a relationship of y equal to half g, which this is a constant again, so you may name it as k or whatsoever, x squared. So you can see this is a relationship that we're looking for, and again this is not in the form of linear line. Linear line is y equal to mx plus c, so it is not the case. So since both of the theoretical framework and the empirical data give you a very strong signs to tell you that it is not a linear line, so let's try to see what else you can do. So let's try to pick it again, and I think we can choose the line itself, and then right click format trend line, and then you can see there are different options: exponential, linear, logarithm, polynomial, power, and something called the moving average, which is not relevant in physics. You may be wondering why is the exponential and power got grayed out in Excel. I also didn't know, and I just go and Google, and I find out for some reason the software is somewhat, I think it's because of the maths issue. They can't handle the data if within your data sets there's a zero, like pure zero there. So they can't do it for some reason. If there's a zero there, they can't do exponential and power equation. Although I'm not looking for that, but then let me just show you how you can do that. So say the main issue is these two cells, right? Because both of these are zero. So one way of doing it is you can try to fix the system, alright, by just inputting a non-zero number, but a number that's very close to zero. So this shouldn't affect our lab report much. So should be okay, I would say. Alright, and then if you try to look at the option again, now you can see it appear again, alright, powered and exponential. So this is some tips for you when you may need to use this in the future. So what you can do is try to look at other options. So exponential obviously doesn't fit at all. Logarithm, again, it doesn't fit at all. Polynomial, it actually fits perfectly because I kind of make up the data, of course, honestly. But even if you try to change one of the data, let's say I change 2.4 to say 3, then this is a bit off. I mean, the whole trend is still quite nice, right? So let me just keep it like this. And let's say we have got powered, and I don't think it matched. And moving out average is something else. Again, we don't consider that in physics. So I think we should go with polynomial. And not sure how much you know about Excel, you can actually display the equation here by clicking this button. For Google Spreadsheet, it's more or less the same, right? But then the button may just be placed at somewhere else. And so this is the equation that we are looking for. And let me just make it bigger maybe, alright, so that you can see easily. Okay, so you can see this is not perfect, alright, this is not exactly what we want. But then if you try to look at that, then you can basically take these as very close to zero, right? So basically you can ignore them. And if you look at these coefficient, then you can kind of compare these two, and probably you can find out g. So if you really try to do that, then you can say 4.8xx1 equals to half g, and if you use the calculator, then it would simply be times 2. Then you can find g is 9.7762. But then in our calculation, in fact, time only has one sig fig, right? So I think at most we can claim one, or at most really two sig fig. So 9.8, alright, or even 10 simply meter per second squared. And so you may be thinking, hey, then I can finish this experiment, right? Why do we still bother to learn something called linearization, right? Which is the main focus actually in this video. Of course, there's a very essential reason for us to learn linearization. So first of all, if you're still wondering what is linearization, and that is when we have a curve like this, how we can turn it straight, right? Literally, like turn it into a linear line. That's linearization. Why? So why do we have to do linearization? If you recall what we have learned so far in chapter 1, we talk about error propagation so that we know the absolute uncertainty, and also we do error bars on the graph, and also the max min line. So in case you haven't learned that yet, you should go back to the playlist and go for maybe part 8, which is a previous part of our playlist, and learn what it is about error bars and max min line. And so for our case here, since when you have certain experiment, you just really have a relationship that is in a curve shape, right? So for example, like this one, then you can't force it into a linear line. Like we said, if you force it, it just doesn't match in both empirical data and also the theoretical framework. So you can realistically change it into a curve without losing the meaning or matching the data itself. So after that, then if you can turn it into a straight line, then obviously you could find out the max min line, and therefore you can find the range of whatever the slope representing in physical meaning. So in our case, very likely the so-called slope that we will find will help us to find out the gravity due to acceleration due to gravity. Then we can find out the range from our experiment. So it's not just 9.8, right? This is like in IGCSE or junior secondary level, you just find out the number, but then you don't know how far this data is valid. So if we can find out 9.81 plus or minus 0.2, for example, then we are very happy with that. So before that, we must get this curve into a straight line. Alright, so let me show you how we can do linearization in our example. Notice that if you are doing some other physics experiment, studying other parameters and physical quantities, their relationship may not be y proportional to x squared, and there will be a slightly difference when you handle them. Or even if you don't know the relationship at all, then there will be another approach I'll tell you later on. But let's say for this example first, what we should do for linearization. Alright, since this screen is kind of messy, I want to clear this up, so I just start over with the new sheet in my Excel with the same data. So once again, what you hope for when you try to plot the graph is you want to get a straight line, a linear line, so that you can draw the max min line later on with whatever error bars you can construct. So the thing is, how do we plot then? Since we now know from the theoretical framework and also from the empirical also, right, you find out, oh, this is the equation that probably will fit to represent the data, and so we should find s and t square to be the graph. I mean, if you don't plot s against t, you can actually plot s against t square, right? And in that case, you should get hopefully a straight line with the slope that's equal to half g, and using that with the max min line somehow, no, not like that, somehow like these probably, then you can find out the range of g later on. And so what we should do here is we need to start a new column, and since we want to find t squared, right, so maybe I will actually insert here, and then I will do time square and then time square. That's a place in Hong Kong, by the way, right? No pun intended. Okay, and we want to find out the value of these. So the easy way to do is you can just calculate from each of the time that you have from your raw data. And I don't know why in the past I've seen students just literally get the calculator and press every single one, like 0.8 square is 0.64, etc. You do for every single one of them. I don't know why. I thought you have learned this in IT lesson, but then let's say if you don't, then I'll show you very quickly. So what you can do is you can insert the formula. So say I call this cell equal to this, which is A2 square. So this is a square syntax. And so here you go, you got 0. And what you can do is you can do Control C, which is copy, and Control V, you can then copy to all the cells here. And so it just be automatically calculated for each cell automatically. So now it is the most exciting part, because you are going to plot the graph, and here we go. Hopefully, again, the title and label stuff we can handle it later. It's actually very good. I mean, yeah, because I make up the data. But then even if it's not, then I guess it's still okay. I mean, if it's off by say 4 for this one, again, it's just one data. I mean, then you can obviously tell this is anomaly. But if you take more data, you can tell it's always better if you can have more data. Anyway, my main point is now you should be very happy with this linear line, and then you can display the equation. And here we go, you got the equation here. And this is not the end. Remember, in the actual situation, you should be able to deduce the error uncertainty for both displacement. So for displacement, probably it's just the last digit, which is plus or minus 0.01 meter in our case. As for the time, of course earlier, like we said, it's probably plus or minus 0.1. And so what you can do is for time square, no pun intended, then you can use what you learned in the previous video about error propagation. So that is to say, if you recall, since we want to find out the uncertainty for time square, then you should have time square log equal to 2 of the delta t over t log, right? So by using this equation, you'll be able to find out for each of these time their own uncertainty. So let's say we have done that and we somehow find out for each of these data their respective uncertainty, and in this case you can then find out the error bar for each of them. And again, this is plotting the error bar is not the main focus in this video. There will be probably another video, and actually there are many videos about how to plot the error bar, so you can go and check that out later. But the most important thing is with the error bar, which you find by error propagation you learned in the previous video, now you could draw the max mean line. So probably something like that, and the other one like this. Then you can then find the respective slope for each of these lines, and in that case you can then find the range for the g. Alright, then that could be very meaningful when you make the conclusion in your lab report. Okay, so now I hope you understand how linearization can be done with our example earlier. So let's try to look at other relationship in physics and see whether or not you can think of the way to get them to be linearized. So for equation that is already linearized, and it's very simple. For example, if you have Hooke's law, I think Hooke's law is not here, but then it's F equal to Kx, and so if you simply plot the force with the extension, then you already get a straight line, so there's nothing you can talk about linearization. So let's try to find maybe there's some equation that is not linear at the first place. So for example, if you see, I think in chapter 6 later on, you have a equation about gravitation. So force, you find out force is proportional to 1 over r squared, and this is called the inverse square law. If you try to plot the equation with simply F against R, I think what you get should be something like this instead, right? When R become bigger, yeah, I think that's what you would get. Instead, it's a curve. All right. If you don't trust me, just go ahead and try to plot y equals to k over x squared, all right, on the graphical calculator, and you'll find out. So my question is, if you want to make this graph to be linearized, what graph should we plot? The answer should be very simple. You just have to plot f, since as we know again f proportional to 1 over r squared, then you just change it to 1 over r squared for the x-axis. Let's try to locate another equation, and that is the Snell's law, which I want to talk about because this is quite special, right, within our curriculum. So think about a refraction experiment, then you may have your independent and dependent variable to be incident and refracted angle, so that may be theta 2 against theta 1. And if you simply plot that, you don't find a straight line obviously, because probably you have done a Snell's law experiment before and you know that's true. And so the relationship between these two angles will be more like a curve like this. And again, how do we linearize it then? Again, it should be very obvious to you. What you can do is you can instead, according to the formula, then you can plot simply sine theta 2 and sine theta 1. Alright, so that means in your Excel you have to find out the value of sine theta 1 and sine theta 2 first and just plot them up. And you probably will find a straight line in this case. And if you're wondering the meaning of the straight line, then obviously it will be the ratio of the refractive index, which is supposed to be constant in the experiment of refraction experiment. Alright, here's another equation where we talk about the period of the pendulum swing. Right, it will be t, and actually it's governed by the equation that is 2 pi square root L over G. L is the length of the pendulum itself and G is gravity, obviously. And so let's say I have to try to do an experiment on this, and I measure the length first as the independent variable and the time later on as dependent variable. So according to this equation, I should expect the result to be t proportional to root L, right, which should give me a curve, I think, like this, right? When L increase more, yeah, I think that should be the graph shape. So again, how should we do if we want to linearize this graph? Alright, it should be very obvious to you now since you have so many examples. So it should be t against root L, and obviously you should get a straight line. And the slope, by the way, do you know the meaning of the slope? The meaning of the slope should be 2 pi over root g, right? 2 pi over root g will be the meaning, physical meaning of the slope. Alright, let's move on to the last important question about linearization. And this question is going to be very helpful to you because you may probably face the same thing when you do your internal assessment in the future. So let's say when you do an experiment, you don't know its relationship at all. So normally when you do an experiment, you probably can do research, and maybe the research from other people, of course, can tell you the relationship that you are looking for primarily. So for example, here is an equation for wind power. So the power here is talking about how much wind power can be generated in the generator when you have that much of area of the wind turbine, density of the air, and also V is the speed of the wind, or speed of the air, let's say. So let's say you didn't know this, all right, and no one ever have studied this before. Of course, this is kind of ridiculous, but let's say we never see this equation before. So what can you do then, right? Let's say your independent variable is the V, because you kind of adjust the wind that blows into the wind turbine, and then you try to use maybe a certain way, maybe measuring the voltage and currents to find out the power. So power is the dependence variable. And so when you try to plot the graph, of course now we in our mind we know there is an equation, but then if you try to plot that, then you will find out there should be a curve like this, right? And you don't know because if you try to fit a straight line, of course it doesn't look like that way. And if you try to fit a quadratic equation, for example, it doesn't work, and also the polynomial with the order of 2, it doesn't fit. And maybe when you try 3, it kind of correct, but then you're not sure. And maybe you fit the order of 4 with polynomial, it also kind of fit as well. So you kind of struggle between which mathematical model you should be using for this data. So let me teach you there's actually a very effective way of solving this, even if you don't know what equation actually between the power and velocity. So the answer is actually logarithm, log function. Have you ever thought of the actual use of log function when you learn it in mathematics? Here is one of the application. So what you can do is you simply plot, alright, instead of plotting P and V, you actually plot log P and log V. Okay, I'll show you why. And these supposedly should show us a straight line. Alright, to make it more authentic to you, I decided to make up the data and also try to plot it to you so that you can trust me that when I plot log P against log V, it will really be a straight line. So of course the data are based on the formula that I find on the data booklet, but I assume, again, when you do the experiment, you didn't know that's the formula. So when I try to plot this, I would find out, of course, it is a curve. And if I try to add the trend line, of course it should be polynomial with to the order of 3, and so maybe that would be good, but maybe there are times where the the data is simply more ugly, so maybe it's like 700 and 1100, so it kind of falling apart, alright, and that may cause a big issue when you try to justify the line. And so when you try to draw the line and you don't know, maybe when you are doing the order of 4, actually it looks justified too, right? Because when I show, this is in the order of 4, it kind of matched too, doesn't it? Right? At 5 and 6, actually there's not much different. Well, 2 you may say, here you can see at the beginning it doesn't look right, but then for 3, it looks fine. 4, 5, 6, so you don't know which one that you should actually use. Who knows, maybe it's to the power of 4 actually. So that's why learning how to linearize it and using the log function is very important. So let's try to plot the graph of log P and log V. So we have to construct the new data table, which is of course process data. And for simplicity, I'll just name it like this. Of course, you can make the heading better with a proper unit and the name. And so what you have to do is, again, using the built-in function in the Excel, you can just go for log this, right? Because we want to have the respective cell to be working. So here is the one. Oh, you can't log 0. That's right. You can't log 0. So we can actually ignore that. Right? It doesn't really matter for the 0. Like that's the beginning of the point. And same for P actually. Alright, you may want to double check that. That's the same number corresponding to the P. And then just to show better in maybe later on when you do it in your report, you want to keep the sig fig to be 2 maybe. And so what we can do right now is we can actually try to plot this onto the graph, right, which will have this, and it actually looks like a straight line, don't you think so? And I think this is a pretty fair line. Of course, once again, you can find out the uncertainty of the log V and log P, and therefore you can find out the error bar of this graph. Okay, this is log P against log V. And in case you don't know how to find out the error uncertainty of a log function, go back to the previous part of my video, or I'll put a link in the description below as well. But because of the time, I'm not going to do those error bar, and I'll just say this straight line is the valid one. So what I can do now is I can find the straight line equation, which is a linear line equation, that is y equals to 3.002x plus 0.1476. The most important number is the coefficient sticking with x, that's 3.002. Let me explain to you. In order to understand this, you have to understand the basic principle of using log function. So what we could do is we can take log on both sides of this equation, and so what you can get will be log P, because power is P, right? So log p equals to log the whole thing. I'll try to do it slowly. A rho v to the power of 3. So if you try to move on with this equation, then you will get log p equals to cos, again in our experiment, we're trying to get p and v to be the variables. That means a and rho will be constant, will be the control variable. So in this case, what we can do is we can separate them. Log half a rho plus log v to the power of 3, and then you should know in your math lessons, you know this will be you can move the index forward. Okay, so that is to say, if you compare the equation here, this one, with our graph that we plotted actually, then log p would simply be the y, log v would simply be the x, and then 3 will be here, and then there is a constant which equal to log half a times rho. So that is why when we try to plot the graph just now, this one, when we find out the coefficient with x is 3.002, we are very happy, because from this graph it shows a very strong signal that the index of v is going to be to the power of 3, right? Because this is exactly the number that is shown on our equation here. When I get to learn this the first time, I was really mind blown, because I finally understand why we have to learn log function in maths now. Lastly, let me show you how we can apply this method, the log function method, into the general situation. In fact, this method can only work with power equation or polynomial. So in power equation, then you may have y equal to kx to the power of n. Okay, so this is a general formula for a power equation. And so if you think about our approach, what we did is we take log for both sides. So once again, you got log y equal to log kx to the power of n, and in this case, then you can separate them like we did, log k plus log x to the power of n, and you can move the n here. And so that is how, when you try to plot the graph of log y and log x, you will get, once again, the straight line, and the slope of this straight line is gonna be n. And actually, if you have a non-zero k, actually not non-zero k, I think if you have k to be it doesn't matter about k, it's actually about log k. So if log k is not non-zero, then what you should get is probably something like this, right? So that will be the y-intercept, and the slope will be n. So if k for some reason is representing any sort of physical meaning, so just like what we have earlier, the physical meaning of our line, like what we have in the previous graph here, this is 0.1476, right? The meaning of this would simply be equal to log 1/2 rho. So you can actually try to calculate things from there as well. So back to the general situation. So that means if you can find out the slope of log y against log x, that means you can find out the slope, which is the end, and then you can then go back to guess what is the power index of the original equation. If you want to see whether or not you fully understand what we cover in this video, I strongly recommend you to go and check out our notes on page 16 and 17. I have given you a set of questions which is based on the real IA scenario of one of my students, and this is his IA data. So I want you to see how you can linearize it and also try to analyze some basic ideas. So go and check it out before you watch the next video. Alright, so that's all for this part of video. In this video, you learn about a few things. First, you learn how to use Excel, basically how to show a proper decimal place, Second, you learn how to plot a graph, maybe if you didn't know how to do that. Most importantly, how you can turn a curve into a straight line in different scenario. You also learn how to apply the log function when you don't know what the equation is. Okay, so that's all for this video. If you enjoyed learning with me in this video, please thumbs up and share this video to your friends. Subscribe to my channel if you want more content. I'll see you again in the next video for explaining the question in the note. I'll see you again next time. Bye.